So, properties of limits is what we're going to look at today. There are many properties of limits that we are going to use, a few of them that we have already kind of looked at. So, the first one that we have here is called the sum rule. And so, they tell you here from the beginning that the limit as x approaches c of f of x equals L. And they also tell you that the limit as x approaches c of g of x equals M. Right? So, if we are finding the limit as x approaches c of f of x plus g of x, I'm going to write this over to the side just to sort of like further explain. That means that we're doing the limit as x approaches c of f of x plus the limit as x approaches c of g of x. We can find those two limits separately and just add those limits together. So that L is your limit as x approaches c of f of x. The M is the limit as x approaches c of g of x. So that rule is going to apply in any situation that we're dealing with limits. A very similar rule is true for subtraction. So the difference rule tells you pretty much the same thing, except for if you're subtracting, then you would have L minus M there, right? So the limit as x approaches c of f of x minus the limit as x approaches c of g of x. And if we have a constant, so in this case, k here is a constant number, so it might be like 2 or 1 or 0.75, 3/4, something like that. Any constant right here multiplied by a function, we can basically just pull that constant out front. So it's going to be that constant times whatever the limit is for that. That will become useful to us on some of the different things that we do. Product rule, very similar to sum and difference. If we've got two functions that are multiplied together, we can just multiply their limits together. We can have limit as x approaches c of f of x times limit as x approaches c of g of x. And quotient rule, this also applies for division. So you can do the limit of the top over the limit of the bottom for this. You do have this condition here. The limit of the bottom function cannot be 0. Why is that? Cannot divide by 0. Right? So if that is the case, you would just say that the limit does not exist because you can't have that 0 in the denominator. The power rule tells us that if we have a limit of a function raised to a power, we can just take that limit, whatever it is, and raise it to that power. Right? N would have to be a positive integer. If it's negative, then that means that you're moving that negative exponent down to the basement, and it changes what the problem is like. And then you really could include this rule with the power rule if you just use fractional exponents, but the root rule, for any root here, you're also going to just raise that, take that square root of that limit, or you can see they did include that fractional exponent there if you think of them like that as well. And for this one, because of the nature of roots where you have to take the square root, when you take the square root of something, it must be positive or 0 or greater than 0, we should say. Can it be 0? They say greater than 0. I do not know why it cannot equal 0. I feel like that should say greater than or equal to. You can take the square root of 0. But I copied this straight out of a textbook written by people who are much smarter than me. So I'm not 100% sure that that's the case. So that won't be terribly important for you guys there. So these are our properties. Let's look at what types of questions we're going to have and what we're going to do with these here. So we have in this case, two functions, f and g. And they give us this information that the limit as x approaches 2 of f of x equals 5, limit as x approaches 2 of g of x is 6, limit as x approaches 4 of f of x equals -1, limit as x approaches 4 of g of x equals 9. So that is just given information that they have given us here. So this very first one, I'm going to break it down into like the theoretical steps of what's happening here, but we won't do that on all problems because these can be done much more quickly than what I'm going to show you. So the quotient rule tells me that if I have f of x over g of x, I can just take the limit of the top and the limit of the bottom. I also have this coefficient right here, which they tell me can just be pulled out front. So what that means is this problem can look like this. That coefficient can be out front. I'm finding the limit as x approaches 2 of f of x. And then on the bottom, I'm finding the limit as x approaches 2 of g of x. And these pieces right here are given to us up here. So we've got both of these pieces given to us. We just have to plug in those numbers. So we've got 2 times 5 divided by 6. So 10 over 6, which of course will reduce to 5/3. Now, when I do these problems, I typically do not write out that limit notation with them. I do that part in my head. So if we do that on the second one, I know I'm taking the limit of these separately, plus I have this coefficient right here. So the limit as x approaches 2 of g of x, that is 6. And then I've got that 3 as a coefficient that's just going to be pulled out, so it's going to be right here. And then limit as x approaches 2 of f of x is going to be 5. And so I get 6 plus 15, which is going to give me 21. I will say this problem would probably be better if I had some brackets right there, because it's up for debate on whether or not the whole thing is being taken the limit of, or just g of x if you don't have those brackets there. So let's put that there to be a little more precise. Questions so far? All right, for number 3, I've got the limit as x approaches 4 of f of x minus 2 squared. So I can take the limit of this f of x minus the limit of the 2, but since that's just a coefficient, it will be 2. And then I can square it. So limit as x approaches 4 of f of x is just going to be -1. So this is going to be -1 minus 2 squared. That will give me -3 squared, which will give me 9. And I should probably have some bracket. Well, yeah. Whether or not I have brackets is really important, especially for this one. Because without brackets, it really probably should be assumed that only the g of x is under the square root. Even though I think you get the same answer either way, but it does make a difference. So, sometimes. So, let's put the brackets here to say that whole thing we're taking the limit of. So, limit as x approaches 4 of the square root of g of x. We know the limit as x approaches 4 of g of x is 9, so what we're going to get here is the square root of 9 plus, and here we just have a 4. So square root of 9 is 3, plus 4 is going to give us 7. Okay. Any issues here? Right. Okay? Now, these can be a little bit more confusing. So, the limit of a composite function. So here, composite functions, that's when we're talking about this right here, f of g of x. So, if we are doing the limit as x approaches c of g of x, we get L. Limit as x approaches L of f of x equals f of L. So, whenever we have the limit of f of g of x, we want to do the limit of the inside part first. So we would find the limit as x approaches c of g of x, and then, because the limit as x approaches c of g of x equals L, then we can do the limit as x approaches L of f of x, which is going to give us that f of L there. So we're going to do the limit of the inside part first, then we use that number that we get to do the limit of the outside part. And there's going to be a little trick to it here. This time I actually have equations, and let me think for a minute. Did I use Desmos on or did I just plug in? We really haven't done any algebraic stuff yet. So let's use Desmos. I think that's what I did before. And I'm going to pull this up here. You guys don't have to get out your computers. We'll look at it together. Alright, so let's do f of x equals 2x minus 1 and g of x equals 1 over x plus 2. Alright, so our red graph is our f of x, our blue graph is our g of x. Let's make this bigger. There, okay. So if I'm doing the limit as x approaches 3 of f of g of x, I need to look at g of x at 3 first. Let me zoom in a little bit here. So at 3, right here, we're going to this point, and we get 2.3 repeating. Okay, so when we do the limit as x approaches 3 of that g of x, we get 2.3 repeating. Now, that means that we've got to look at where f, so now we're thinking the limit as x approaches 2.3 repeating of our f of x. Now, there is a little bit of a trick to this. So, on this graph right here right there at 3, if I can ever get back and never return to the perfect 3 that I was at. There we go. Right there at 3. Are our values, as they approach the 2.3 repeating, are they coming from above or below or both sides? So we're thinking about our y values, and we're also, this is not a one-sided limit, it's from both sides. So as we approach this point right here, is our graph coming from above, below, or both? Both, right? On the left-hand side, we're approaching from above. On the right-hand side, we're approaching from below. So that means this limit is going to also be from both sides. Okay, so as we approach 2.3 repeating, it's from both sides. It really doesn't matter on this particular graph whether you think about that or not, because it doesn't become an issue. But if I go to over here on this graph, I'm pretty sure I'll never get to 2.3 repeating exactly. How could I figure this out? how could I figure out what the y coordinate is there at 2.3 repeating? If I want to know the y coordinate on f, because whenever I try on the graph, I can get 2.3, 3.6, 3.4. It's probably about as close as I'm going to get. How could I get the exact value? Just plug it in, right? We'll use Desmos on these, even though you don't have to use a calculator, but if you type in f of 2.3, it plugs it in for you, or you could just do 2 times 2.3 repeating minus 1. So it looks like we're getting 3.6 repeating for that. So we get 3.6 repeating, and that is our answer. All right, so questions about that one? For the second one, we've got the limit as x approaches 0 of g of f of x. So this time inside first, so we're thinking, what is the limit as x approaches 0 of f of x? All right, so f of x is our line here at 0. We have a y coordinate of -1. We could also get that just by plugging in 0, right? So we get -1. Now, we're going to think about it, although it doesn't make a difference on this one. Does that approach from just the top, just the bottom, or from both sides? Both sides, right? We're approaching from the bottom over here, approaching from the top over here. So that means our next limit that we're going to do, which is our limit as x approaches -1 of g of x, is also going to be from both sides. And so over here, at -1 on our g of x function, we are getting a +1 at that point. So that would be our answer here. Okay, questions? Mm-hmm. More or less, unless we have to think about the direction that it's coming from. So in this particular instance, it does not matter that it's from both sides. So it works out. Now, if we were looking at, like, let's say that we got 0 right here, it would matter about whether or not we're looking from both sides, right? Because at 0 on g of x, from the left side, we have a different limit than we do from the right side. So that would change what your answers could possibly be. But more or less, you're plugging into this inside one first, whatever you get here becomes the value you're approaching for your g of x, which means you're going to be plugging that one into g of x. Okay, these are ones that can be done with direct substitution, just meaning you're just plugging in that value. So it creates problems where you are just plugging in. There will be some more that are a little more complicated we'll look at next. For 3, what is the limit as x approaches 0 of g of x? What is that? It does not exist, right? Because from the left you approach negative infinity, from the right you approach positive infinity. So it does not exist. So if you get does not exist here, that means the whole thing does not exist also. Okay, questions there? All right, this one has us a couple graphs, and here's where things are going to get a little bit weird. Okay, so to do this problem, we've got the limit as x approaches 0 of f of h of x. Make sure you pay close attention to which one's f and which one's h here, especially when you do your delta math on this, because delta math sometimes will put f first and g second, and then sometimes we'll put g first and f second. So there's not like a standard way they're listing those, and you might be looking at the wrong graph. So watch out for that. So we would need to look at the limit as x approaches 0 of h of x. All right. So if I look at my h of x graph, what is my limit as x approaches 0? -1. Okay. Now, here's where we really have to think about what direction those values are coming from. Okay? So, these two lines that approach this point right here, do they come from above, below, or both? Above. They're both coming from above, right? So since those values are coming from above, above is going to equal the right, because on the xy axis, our positive numbers are on the right side. So that means when we go to the next step and do our limit as x approaches -1 of f of x, we want to approach from the right-hand side. And it matters on this problem. It didn't matter on the last problem. We were approaching from both sides, first of all. And it didn't matter because we were at a point where it would have been fine to approach from left, right, or both sides. But on this problem, it matters. Because at -1, if I just approach -1 from both sides, I'd have does not exist, right? But if I approach this from the right, so -1 approach from the right, what am I going to get as my answer? Positive infinity. So not only do you have to figure out what the limit is for that first step, you also need to think about, are those values coming from the top, from the bottom, or both sides? Right. Above is going to be right. Bottom is the left, and then both, of course, is going to be both. So because we're looking at this limit here on the inside, we're looking at y values when we look at limits, right? So as we get closer to this point, we're coming from, 1.5, we're coming from the positive numbers here. We're thinking about the y-axis, not thinking about the x-axis here, because we are definitely looking at approaching from both left and right. So we're thinking about what the y values are doing. Right, so both of these lines here, your y values approach from the top.
So because it comes down to it.
Right. And the y values of this problem become the x values of our next limit that we're looking at, so that's why it affects it. Does that make sense? So you're thinking, when you're asking yourself this for composite functions, you're thinking about what are happening with y values. That's why we're thinking, are we coming from above or below rather than left or right? Because on that first one, you'll always be looking left and right. But you want to think about what are the y values doing, because those y values here, -1 was our y value, right? It becomes the x value when we do the next step of the problem. So that's why we care if it's from positive numbers or negative numbers. Okay? This confused me so badly, like the first 2 or 3 years that I taught this. Hopefully I now understand it well enough to explain it to you better than I used to explain it to children, and you will not be as confused as I was whenever I began, but it's a little tricky. And on Facebook there's an AP Calculus Teachers Group. It's excellent. If we ever really get stuck on something, I could go ask it. It's wonderful because like all the like best AP Calculus teachers are on there and respond to stuff. It's like the ones that do all the big AP trainings, like the AP classroom videos, the teachers that do those, like actually like will respond to your post if you post stuff on there. So they're kind of like famous AP Calculus teachers. So I see these questions come up a lot on that in that group. People ask about these a lot, so I think it's probably confusing to some others. I have not actually ever posted in it because I usually can search past posts and find the answer to my question. But it is kind of cool because there's a lot of good stuff on there. It's my favorite there. So if we look at this one, we're doing the limit as x approaches 0 of f of h of x. So we would look at limit as x approaches 0 of h of x first. H of x is the second graph. What value do we approach here? 0. So this is going to equal 0. Are we approaching it from the top, from the bottom, or from both sides? Okay. We are approaching it from the top. So top is going to equal the right. It actually doesn't end up mattering on this problem. Because whenever we do the limit as x approaches 0 of f of x, we need to do this limit from the right. So 0 is right here. As we approach from the right-hand side, we go to negative 1. So that would be our answer. It would not matter if you forgot to think about top or bottom on this problem, because what's the limit as x approaches from the left? Also negative 1, right? So you could get away with, what you'll find is like there are times that you can get away with not thinking about that top and bottom piece. But you will probably run into it, if you don't ever think about it, you'll run into a question you keep getting wrong, and you can't figure out why, and it's because of that top and bottom piece. Yes? What, over here? Oh. Right here? We are only looking at where x equals 0 on this graph. So our x equals 0 right here. So we're looking at as we approach from this side and from this side. So you're looking at the points closest to it. It may go below on the other side. So like you are, like over here you're below, and then you're above, and then you come down from above. But you're looking at whatever's happening at the points closest to it. Does that make sense? So it may do something else crazy over here, but you only care about those points near it. Okay, questions? Okay, let's look at this one. This one only gives us one graph. It gives us f. And we are asked to find the limit as x approaches negative 4 of f of x. So this time what we're going to have to do is we do the same thing we did on the last problem, but we're just referring back to the same graph both times because it's f of x. You're composing a function with itself. So we would do the limit as x approaches negative 4 of f of x. And the limit as x approaches negative 4 would be right here. There's our negative 4 of f of x. What is our limit there? Negative 1. Okay. Are we coming from the top, from the bottom, or from top and bottom? We're coming from the bottom, right? So near that point, we're approaching from the negative values, from the bottom. So since it's from the bottom, that means whenever we switch to x values, we're going to be coming from the left side. So we would be finding the limit as x approaches negative 4 from the left of f of x. And you can see it would matter on this problem, right? On the last problem, we could have gotten it right even if we neglected that. It matters on this problem because right here at negative 1, if we approach from the left, what value are we going to get? Negative 5. But if it had been from the right, we would have gotten positive 4. But it was not in this case. Oh, yes, thank you. That's what I was doing on my graph, but I didn't write it correctly. Yes.
If you continue to do f of x, f of x, will the numbers start to repeat themselves, or will it be completely random?
It's going to depend on what function you have. Like if we did this again, we would be finding so if let's say it was f of x, right? So let's see, this time we approached negative 5 from the top, right? So we'd be doing limit as x approaches negative 5 from the right of f of x. So that would be at negative 5 right here, we'd get negative 2. And then you'd keep going with that. So it would just depend on what your values were for your function. For some functions, it may eventually end in does not exist, or it may become repetitive. For others, you could just get random values for a really long time. It just depends on what equation you've got. That's a good question, though. Okay, questions here? All right, so we have got 2 things that we're going to do that hopefully you'll have time to do most of this in class. In your book on page 84, we are going to do 37 through 44. This is it says homework right there, but this is classwork. We're going to check how we're doing on this before we go. So this is going to be kind of like what we did at the beginning. You may use Desmos on this if you would like, because a few of them have those equations, and you can use Desmos if you would like on those. You should not need Desmos on like 41 through 44, but on 37 through 40 you may. Then the next thing you will do, we will go over these problems before we leave. So I'm gonna let you guys work. If you get that done, go ahead to the Delta Math. But before we go, we'll run through them and see if we have any questions. Then your homework assignment for tonight is from Delta Math. And let me change it so it lets me see it like you will see it here. And it will be this limit properties graphically. And it's going to have problems like those last ones we were doing. Some of them might be f of g of x. Others could be f of x plus g of x, f of x minus, something like that. Also, on Tuesday, we are going to have a quiz on 1.2 through 1.5. So, it will be on Delta Math. Because it is our very first calculus quiz, and because I'm giving it to you on the Tuesday after a break, which is not the ideal timing to have a quiz, I have put up a practice quiz here because Delta Math is pulling from a question bank, so it's not going to give you the exact same questions, but it will give you similar questions. This is optional. You do not have to do this. It's not a homework assignment, but if you would like to work through it, it is going to give you questions similar to what you will see on the test. I do want to look at one of these right here together first because I just want you to see how this works. So, the table values, I think we did do this in pre-cal maybe. I don't know if it did both semesters or just one. But it's asking you to find the limit as x approaches 1 from the left. So from the left, you need numbers smaller than 1. So 0 would be a possibility, and then maybe 0.5, and then maybe 0.9. Uh-oh. What's it doing? Okay, 0.9, 0.999. Oh, this keeps, I gotta delete it on 0.99, 0.999. Add another 9. All right, so what does it appear to be approaching from the left? Looks like it's going to be 3.5, right? Then you can clear out the table and answer the next part. From the right, you would need to approach, from the right, you would have like 1.1, 1.0, 1.01, 1.001, 1.0001. It appears that you're also approaching 3.5 here. Because those are the same, you'd have 3.5 here. It's possible to get does not exist if they don't approach the same value there. And then to find f of 1, you just type in 1 here, and it tells you that it's actually -5. So you've got a limit that approaches something, but you got an actual extra dot over here, out here in space is what's happening for this graph, right? So you'll approach from the left, approach from the right. If those are the same, you'll get the same number here. If they're not, you'll get does not exist. And then for f of 1, you would just plug in that value. So that's what you'll do for those problems. It's like the calculator, it's just that you don't have a function to plug into y equals. They're not telling you what the actual function is for that. The rest of them should be pretty self-explanatory there. It is optional. You do not have to do it, but it's up there if you want. I need to make it where that quiz doesn't show up yet because I don't want you doing that quiz. So, do these from the book first. You are always welcome when we get to independent work time to work with someone else if you would like, with your buddy, or if you want to ask someone else